Welcome to This Explainer. Today, we're going to unravel a really terrifying climate mystery from our past, all to help us better understand our future. We usually think of climate shifts as these slow, gradual things, but today we're looking at a sudden, incredibly violent change. We are going back to a time when the sky just darkened, summer quite literally never arrived, and the entire world was pushed right to the brink.
Okay, so let's set the stage. Picture this, it's 1816. You're expecting warm, sunny summer months. But instead, these bizarre anomalies completely reshape the world around you. Let me ask you, what on earth could possibly connect the invention of the bicycle, the writing of a legendary Gothic horror novel, and actual snowstorms in July? Well, it was a massive domino effect, and a truly bizarre one at that. In 1816, a sudden climate shift froze summer crops dead in their tracks. We're talking snow unexpectedly falling in New England right in the middle of summer, and this gloomy, freezing rain just blanketing Europe. This extreme weather sparked widespread food scarcity, and because food was so scarce, the price of oats absolutely skyrocketed. Suddenly, feeding a horse became way too expensive for the average person. This literal transportation crisis is actually what inspired a German man named Karl Dreis to invent an alternative way to get around without a horse. And yep, that was the very first bicycle. And the impacts didn't stop at agriculture and transportation. They profoundly shaped the culture of the era too. These endless dark rains locked people indoors for days. During a vacation at Lake Geneva, writers Mary Shelley and Lord Byron were trapped inside by the constant rain and bleak skies. That dark, claustrophobic environment directly inspired Mary Shelley to write her masterpiece, Frankenstein. It also led Lord Byron to pen his haunting poem Darkness, perfectly capturing the apocalyptic mood of a world where the sun just vanished. But to find the real culprit behind this frozen summer of 1816, we actually have to look far away from the icy farms of New England or the rainy estates of Europe. The trigger for this global catastrophe was hiding on the exact opposite side of the planet, over in Indonesia. Let's look at how this built up from a local disaster into a global atmospheric shield. On April 5th, 1815, Mount Tambora began to rumble. Over the next 4 months, it unleashed the largest volcanic explosion in recorded history. Now, the heavy ash caused immediate local destruction, for sure, but it was the smaller particles that spelled disaster for the rest of the globe. These tiny particles shot straight up into the stratosphere, where they caught the winds, wrapped around the entire world, and effectively blocked out the sun. To really put the scale of this into perspective, the eruption injected an estimated 60 teragrams of sulfur dioxide into the stratosphere. Up there, it converted into this massive, highly reflective sulfate aerosol cloud. It essentially acted like a giant planetary mirror, bouncing incoming solar radiation right back out into space. And you can see the immediate, localized freezing effect as the sky darkened. Temperatures absolutely plummeted, especially over Western Europe, which experienced severe cooling, dropping as much as 4 degrees Celsius compared to historical averages. But the absolutely crucial point here is that this wasn't just a localized chill. Earth's average global temperature dropped by a staggering 3 degrees Celsius. To put that in context, that sudden drop is roughly equivalent to the entire net global warming the Earth experienced over the 20th century, just moving in the exact opposite direction, almost overnight. Now here is the really fascinating scientific twist. As catastrophic as 1816 was, with the famines, the dark skies, the freezing summers, modern energy budget simulations reveal an unsung hero. Something massive actually prevented an absolute world-ending climate apocalypse. To understand what actually saved humanity, we need to look deep underwater at something called ocean heat content. Think of this as the massive thermal battery of the world's deep oceans. Here is exactly how the oceans saved the day. First, those volcanic aerosols blocked the sun, right? Normally, without that solar energy, the global water cycle would just completely crash because you need heat to evaporate water and create rain. But back in 1815, the ocean was relatively well mixed. This means it was able to quickly release deep, stored heat upward, an absolutely astronomical 70 sextillion joules of it, just to buffer the atmosphere. This incredible release of heat acted as a lifeline, sustaining global evaporation. The deficit from the blocked sun should have crashed the global water cycle by a massive 8%. But thanks to the ocean releasing all that stored heat, the actual global rainfall drop was less than 3%. The ocean stepped in as this giant thermal battery, keeping the Earth's hydrological cycle from completely flatlining. So, We know how humanity survived 1816, but this brings us to a really vital question that recent climate models have been exploring. What if a Tambora-level eruption happened in our future climate, say in the year 2085, under a business-as-usual warming scenario?
Well, the key difference lies in that ocean buffer we just talked about. The 1815 ocean was well mixed. Deep heat could easily churn and rise to the surface. But by 2085, global warming will have drastically heated the upper layer of the ocean. This makes the ocean highly stratified, meaning the warm, buoyant water stays trapped on top, and the cold water stays firmly locked below. Because it's stratified, the ocean can no longer efficiently churn and release that deep heat to save us. And because the ocean's moderating influence is severely handicapped by this stratification, climate models show something genuinely alarming. The peak response in surface temperature drops, and the resulting crash in global rainfall would actually be 40% greater than it was back in 1815. When you look at the climate model simulations, the data really drives this home. In a warmer base state, a massive volcanic shock just doesn't get absorbed as easily. Instead, the surface cooling and that weakening of the water cycle are dramatically, aggressively amplified. Now, you might be thinking, hey, wouldn't a massive cooling event actually be a good thing in a warming world? Sadly, no. It creates a terrifying mismatch. By 2085, background warming might be sitting at plus 4.2 Kelvin. The amplified cooling from the eruption would be roughly negative 1.1 Kelvin. The result? This massive shock wouldn't even offset a third of our accumulated global warming. Instead, we just get an extreme, sudden climate whiplash on top of an already stressed system, complete with radical, unpredictable shifts in tropical storm clouds. It would be absolute chaos.
Which leaves us with this final, incredibly critical point to ponder. If a single eruption in 1816, buffered by a healthy, functioning ocean, froze summer crops and brought the world to the brink of starvation, how on earth would our highly complex, incredibly fragile modern food system handle an eruption that is 40% worse? It's a pretty sobering reminder. As we change our planet's baseline climate, we are completely altering our ability to survive the sudden shocks that nature will inevitably throw our way.